me try. Okay. Okay, good morning. I'm Po-Feng from, now I'm postdoc in the Max Planck Institute in Heidelberg, Germany. So although we're, according to our schedule, we're still in the low Z section, but actually I'm going to redshift 1 about 7 billion years ago. We're not in the Milky Way or M31 anymore. So for this talk, I will show you what we learned and how galaxies become quiescent from deep galaxy spectroscopy. So galaxy spectroscopy, that's how we learned a lot of information about galaxies. So emission lines give you star formation rate and ISM, and those absorption lines give you the information of the stars. But one problem is that doing this is actually expensive. If you go to higher redshift, and if you want to even take the Milky Way mass galaxy, the spectrum of Milky Way galaxies, then you use big telescope, a few hours, then that's what you get. A lot of information is buried in the noise. So we have a crazy idea. We'll say, okay, 2 hours is not enough. Let's do 20 hours. So we spend like 100 nights on VOT, and we take about 3,000 galaxies, deep spectrum, at redshift close to 1. So we achieved the single noise comparable to SDS or even better than SDS's spectrum at redshift 0.1. So many things you can do at redshift 0.1 with SDS's now you can do at redshift 1. We do this in the Cosmos field. You get a lot of ancillary data, and we go down to about the 10 to the 10th solar mass or so. And now we will have data release, and now that's what we have. About half of the sample is already released. Just to give you a quick example spectrum, 2 galaxies. The first one is a star-forming galaxy, lower mass, 10 to the 10th solar mass. And the bottom row is a massive quiescent galaxy, 10 to the 11th solar mass. So from this kind of a spectrum, you can measure stellar kinematics, stellar populations, and larger look-back time, and not for 1, 2, or 10 galaxies, for a few thousand. So you know what's the average population look like. Also, you can get individual variation, get a scatter of the galaxy population. So I can spend the next 45 minutes to tell you about what we can do with these kinds of spectra, but I only have 15. So just to point out quickly 2 things that people have asked or touched in this workshop. So actually we can measure a stellar rotation of the galaxies. We have just sliced through our slit. We get good enough single noise to do this. And also yesterday, as we discussed yesterday, we can measure or we can reconstruct the star formation history by decompose the galaxy spectrum into a stellar spectrum of different ages. So that's just the general idea. If you want to know more detail, just talk to me in this workshop. But in this talk, I will go back to very simple things, just to use simple age-sensitive feature in the spectrum. So here I show you about 1,000 galaxies or so. It doesn't look like quite 1,000, but and color-coded by their specific star formation rate at redshift 1. So the 2 axes, the 4,000 angstrom break, that's roughly age indicator. To the right is the older galaxies, and the y-axis is the delta absorption, the Balmer absorption line. So this is sensitive to about the star formation a few 100 million years or 1 billion years ago, because the absorption line mainly comes from A-type stars. So combine these 2 indices, you give you some age and recent star formation activity in galaxies. We already built up this kind of a good description for local galaxy from a Sloan spectrum back in 2003 or so. And now 15 years later, in 2018, we can do this at redshift 1. So quickly compare these two populations, we can identify a few interesting features. Just one of them is that we find at redshift 1, star-forming galaxies seem to have stronger Balmer absorption lines. And we interpret this as a more burstier star formation pattern at redshift 1, because that's how you get, as I said, is a Balmer absorption line is sensitive to star formation activity just recently. So we interpret it as oscillating or more burstier star formation pattern at high redshift. So that's for star forming galaxy, but now I'll quickly move to quiescent galaxy. But before I jump into the galaxy spectroscopy, let's start from famous mass-size relation and put this into the context. So at a given mass, we know on average star-forming galaxies are larger than quiescent galaxies. So from the current star formation activity, we can say larger galaxies are younger at fixed mass. But then the question is, okay, if we look into only the star-forming galaxy or only the quiescent galaxies, then what do we see? Okay, then now we're still in the low redshift section, so let's go back to redshift 0. And we know for a long time, this is just mass size relation for star-forming galaxy color-coded by their gas fraction. We know for a long time that larger galaxies, actually, they are gas-rich. And these small galaxies, they're color-coded red, so they're very gas-poor. Just very simple expectation is they could be quiescent in the next very recent future. So, and also there are other lines of information saying this large galaxy, they are very low in star formation efficiency. So, okay, look at the gas fraction, the potential they can form stars. Also, you get a similar idea that, okay, smaller galaxies evolve faster. That's a very broad sense. But before I go back to quiescent galaxy, I want to do a little bit of sidetrack because we talked a lot about ultra-diffuse galaxy in the first day. So in this part, there are some ultra-diffuse galaxy. That's a definition by the structure. And for color coding, you can see they are super gas-rich compared to their smaller counterparts. And these are very gas-rich. The gas fraction is like 95%. The gas mass is like 20 to about even 100 times in their stellar body. So when you say these guys are too large for their stellar mass, actually the stellar mass is just a poor tracer for the mass. On the right-hand side panel, if I count the mass of the star plus gas, then they're still large, but they are not extraordinary, right? So for me, I would say for these particular guys, the right question to ask is why they don't form star instead of why they're large. And if some of you were interested in other property of these guys, they are blue in optical. You can see them in galaxy image. They are bright in UV, and they are not in cluster. So they are very different from those coma UDGs. That's enough for a sidetrack. Let's just come back to our main topic, the quiescent galaxies at redshift 1. Now, again, the size-mass relation color-coded by their stellar age, and darker means old, lighter means young. So the first thing is that, we see massive galaxies are older. That's downsizing. But at fixed stellar mass, you see a slight trend that if you look at a smaller galaxy, they are older, and the larger galaxy, they are younger. That's on average. This is smooth. That for each size and mass, there are multiple galaxies, and I take a local average of them. So again, and remind you that the blue band is where the star-forming galaxies are. So again, we see a sort of a similar picture that smaller galaxies, they evolve in a faster pace. First we look at the current star formation rate, and then for star-forming galaxies, we look at the gas. That's the potential they can form stars. And for quiescent galaxies, we look at their stellar age. That's integrated star formation history. We all sort of arrive at a similar conclusion. The smaller galaxies, they evolve faster. But the real world is not that simple, and life is difficult. So if we look at some special galaxies, the post-starburst galaxies, these are the quiescent galaxies, but they have a strong Balmer absorption line in their spectrum. That means their stellar body is dominated by A-type stars. So if you would like to give them a stellar age, that means they are among the youngest quiescent galaxy. So what's their mass? Actually, they are not large. On average, they are smaller than the average. So there's a problem. They do not follow the general correlation between the age and the size. And actually, now we have the two seemingly contradictory statements about the correlation age and size. And these two seemingly contradictory statements has been repeatedly reported by many studies, including, I think, one of the authors is just sitting in this very room. So like the people point finger to each other and ask who messed up. But yeah, actually observationally, nobody messed up. But just everyone just presents just the partially truth of this universe. Fine. nobody messed up, but how can we reconcile these two seemingly contradictory results? It's not difficult. You just got to know that not every single quiescent galaxy will go through a post-upward phase. In order to get this strong Balmer absorption line, you have to shut down the star formation in a short time scale. So either you had either you have a burst or you don't, but just shut down the star formation, and you have the short period that you get a strong Balmer absorption line. On the other hand, if the star formation rate just declines slowly, then this galaxy will never go through a post-upward phase. So what we see is the size of young quiescent galaxies seems to couple to their the star formation history in the recent past. And this actually require different routes to quiescence. And I want to remind you, I will arrive to a similar conclusion that we find in Redshift 0 like 2 days ago. So first route is that you shut down the star formation in a short time scale, you produce post-upburst galaxy. And if you, let's assume, or you believe the progenitors were star-forming galaxies, they lived here, their effective radius need to become smaller. They need to shrink. But actually, how can you shrink a stellar body? I don't know how, but since we measure the size in effective radius, this matrix means the radius enclosing 50% of light. So the way you make it smaller is you dump some new star in the center, or dump some light in the galaxy center. So the effective radius will actually shrink. So this is how you do it. I show you some image of post-upburst galaxies. You can see there's definitely a bright core, but with some fuzzy and outskirt light. But this is measured in the V-band or B-band frame wavelengths. And just to give you a heads up, you'll hear more about the size of post-upburst galaxy measured using stellar mass profile. I think it's just after the break today. Okay, so I'm not going to point out any particular mechanism to do it. Just pick your favorite, but you got to do this. You got to do the two things at the same time. It's just shut down the star formation, and at the same time, put some new mass in the center. And someone here is smiling, and you already got your favorite mechanism. So that's the first route. But this route is unlikely the only route, because if it were the only route, then you will have the difficulty to explain why you see on average larger galaxy, the younger galaxy are larger. So for this, actually I think you don't need to do something like a dramatic to those galaxies. I would say if you take a star-forming galaxy, and I advocate it's probably more likely those smaller star-forming galaxies, and it's when their star formation dies out, and then sometimes it's so low you'll call it a quiescent. And because the distribution of size of star-forming and quiescent galaxy, they actually overlap a bit. So those smaller star-forming galaxies, if you measure them, their size, they look like a larger quiescent galaxy. So they will just, star formation dies out, and they join the red sequence from the larger side. And if you care, this also the progenitor bias or the evolution of the average size of the quiescent galaxy is at least partially driven by this route. So that's all I want to say. Required by the data, again, I don't point to any specific mechanism, but required by the data, there's probably the two different routes, two different kinds of mechanism, or even if you want to call it a mechanism, two different kinds of mechanism to produce the quiescent galaxy. And then the last note is that the spectroscopy data I show you now, they are all public. So you can go to download the spectrum and do your analysis. We also provide a catalog with some basic information of those galaxies, and also some spectroscopic measurement from the spectra, including the one I use, the 4,000 angstrom break, and the equivalence of the Balmer line. So you can just download it, enjoy it, doing your science. Thank you.
Questions? Thanks for that lovely talk. I completely agree with your point of view. I'd like to point out that there is a paper by Hassan Yusuf a few years ago in which he isolated all of the trends that you've identified in a series of post-starburst galaxies, including the shrinkage of radii. And one of the interesting things that he found out for the galaxies that seem to be early in this sequence, namely just quenching now, was the incredibly large fraction of disturbed objects. And so it really looked as though some mergers or something like that is responsible for initiating this process at low redshift. Anyway, we should consider that.
Yeah, okay, thank you. I should find that paper and read it.
As for the fast track that you are discussing, how different is it from what we call wet compaction, which we see as blue nuggets at redshift 2 and 3? Is it any different or is it similar?
So here, as I say, the reason I don't point to any like mechanism is because from here, just to be honest, I cannot pin down what's the mechanism. But the wet compaction, as you said, is if the result is to put in some new mass and actually make this.
You simply put gas in the middle. The gas make stars, and then the gas is depleted and quenched, and the quenching you put.
Yeah. So this is the very likely mechanism to do this.
Do you know of any other mechanism? Do you know of any other mechanisms to do this?
Not really. All you need to do is trying to put some gas in, funnel some gas in the center, and those gas need to.
That's a trivial mechanism which was predicted by in many papers and was seen in some higher redshifts working.
Yeah. So
Barrow et al. I know this paper.
Yeah, I agree with you. I'm not saying that it's
No,
not.
I'm saying this is redshift 1 equivalent or analog of what we saw observationally at redshift 2 and 3. And what we predicted by simulation.
I totally agree with you. I'm not saying it's not. Yeah, I agree with you.
Oh, of course. That's what I'm asking. What are the differences? Okay. I think what will be very healthy is if you really can point out differences between what you see at redshift 1, which is new, to what we already saw at redshift 2 and 3, and to what the simulations predict at redshift 3, 2, 1.
Okay, so
it's all in paper, and you can see it, and you can relate to it.
Right. So if I can add a few new words, I think my point of view at redshift 1, to make this, you probably need some gas-rich merger, because if you look at the image of redshift 1 post-starburst galaxy, many of them have some disturbed, maybe not crazy, but a little bit disturbed like morphology. So that's a signature for some interaction or merger. And also, if you go to, say, group or cluster outer skirts at redshift 1, you find the post-starburst fraction increase a lot by a few times at least. So those lines of evidence to me is some hint that, say, mergers or some interaction events are producing those post-starburst galaxies.
Yeah, that's very right, because we learned from the simulations that about 50% of the compaction events are caused by mergers. So you're absolutely right. This can be one of the mechanisms, but the more generic thing is putting the gas in the middle, which is the compaction, which can be caused by many other things as well. It will be very nice if you point out those issues here in comparison to the high redshift and to the theoretical prediction.
Okay, thank you. So I will point out to my paper a few years ago. I didn't really think about it by the time, but now I find, yes, just in this paper, I look at the morphology and some other property of the post-starburst galaxy in a redshift 0.9 cluster. And all those, the conclusion I arrived is, at least in that cluster field, the interaction or merger must contribute to produce more post-starburst galaxy. Okay, so.
Yeah, I think we should move to the next speaker. Let's thank again Po-Feng. Our